Okay, for this first question up here, what am I writing down for the chemical reaction? Okay. What else? Really? Okay. State? Okay. And then on the other side? Everybody had iron 3 bromide, right? FeBr3. Why should it have been FeBr3 and not 2 or just FeBr? Three is the one that's most common. So if you look on the periodic table, the oxidation states that are shown are 2 and 3 is bolded. So unless something weird's going on, you're not going to have iron 2 produced. And there isn't anything weird going on here, so it's iron 3. How do I balance this out? What do I need to do? Why? If I put a 3 in front of the HBr, I get my bromines balanced, but that's going to be problematic for me, right? Yeah, I put a 2 here to even my bromines because the problem is those bromines come in pairs. So if I put a 2 there, then I know I have 6 on the right-hand side, and then I can put a 6 over here, and my bromines will be even or matched, and then that gives me an even number of hydrogens to go along with my hydrogen over here to give me a 3, and then I can put a 2 right there. Is that good? Okay, so what I'm trying to figure out is everything that's going to be left in the container after this reaction occurs. So how do I start this process? Start with a given and do what? And ending with what? A product. So you pick one of those 2 given reactants and calculate the concentrate or the amount that you would create for a product. And then you pick the other reactant and do what? Do the same product. Okay. So I'll start with my 125 grams of iron, and then my 1 mole of iron, and what is it, 55? You guys have 845? They must have updated it. Mine says 847 up here. 845. Okay, and then I'm going to go, so what did that first thing do for me? This counted how many irons there are in 125 grams of iron. So now I need to choose one of the products. Which product would you pick? Yeah, just make it easy on yourself, and so you can just take the 1.00795 multiplied by 2. It does not matter, but whatever. So then I'll put moles of H2. So I need to put a 3 here and a 2 here, and then for every 1 mole of H2, it's grams of H2, and it's 2.0159, I think. And this will be grams of H2. So since I have to do the other one anyway, I'll just go ahead and do that before I actually do the math. So I've got 275, and I switch colors. 275 grams of HBr. And then for every 1 mole of HBr, some grams of HBr. 80 something or other, right? 79.904 plus 1.007 equals, so I got 80.912. And then 6 moles of HBr and 3 moles H2, and then 2.0159 grams H2, 1 mole H2, grams H2. Okay, so let's do 275 divided by this 80 number, times 3 divided by 6 times 2.0159, and I get 3.43 grams. And then 125 divided by 55.845 times 3 divided by 2 times 2.0159, and I get 6.77. Awesome. What do I know? What's the limiting reactant? The hydrobromic acid. So the moment that I've made 3.43 grams of hydrogen gas, what happens? This whole reaction stops because I've just run out of HBr. There's no more hydrobromic acid to get this reaction to go any further. So that means I'm going to have some leftover iron in the container. But before I calculate that, I need to figure out how much of the iron 3 bromide I was able to make. So I'll start with my 275 grams of bromine and 80.912 grams of hydrobromic acid, 1 mole hydrobromic acid, 6 moles hydrobromic acid, and then 55.845 plus 79.904 times 3 times 3. Oh. And I get 295.557. Oops, I'm not there yet, my bad. 2 moles FeBr3, 1 mole FeBr3, and now 295.557 grams FeBr3. So 275 divided by that 80 number times 2 divided by 6 times 295, and I get 334 point, I guess I only have 3 sig figs, so alright, 335. Okay, great. Now what? Okay, so I started with 125 grams and 175 grams. So 125, 275, so 400. So 400 grams of stuff went in. How much product came out? Minus 335 and minus 3.43. So I've got 400 minus 335 minus 3.43, and so I get 61.57 grams of what? Iron. So everything that's highlighted in blue, that's what's in the container. Happy with that? So we're going to do the same sort of thing right here. So I'm going to start with 125, 175 grams will be left in container after reaction. Okay, so what do we have for balancing in states? What do you want to do? Put a 10 right there in front of the carbon. Now what? 16 in front of the HCl. 8 in front of the chlorine. Okay, I'm good. So states, what do you think? I'm done with that. Pretty close to 8, which is gasoline. What about the chlorine? Gas. The carbon? Don't get tricked by this last one. What is it? I said don't get tricked. It's a gas. I know that we usually say that the acids are aqueous, but that's when we're using them, right? So if I wanted to go get, like in the last problem, some hydrobromic acid, I'm not going to probably go grab some HBr gas. I'm going to go get a liquid with some HBr dissolved into it. But this HCl, where did it come from? It just came from this chemical reaction. Like it literally just came into being. It was just born. So under normal circumstances, this stuff, HCl, would like to be a gas. So I'm sure if I wanted to capture this, I would want this whole reaction to happen, the output of this reaction to be captured by some water. Okay, so 125 and 275. So really we're just going to do the same thing. So I got 125 grams of decane. Oh, actually that's not decane. I don't know what that is. Oops. What is the deal with that? So 1.00795 times 16 plus 12.011 times 10. So I have 136.237 grams of C10H16. 1 mole C10H16. What do you want to go to, product-wise? I just go to carbon because it's easier. 1 mole C, 12.011 grams of C. So then I'm going to go to 275, if I could write, 275 grams of chlorine, 1 mole chlorine, grams of chlorine, 35.456 times 2, 70.912, and then it's 8 moles of chlorine and 10 moles of carbon and 1 mole of carbon, 12.011 grams of carbon. Okay, so 125 divided by the 136 number times 10 times 12.011. So I get 110.203 grams of carbon. And then I've got 275 divided by the 70 number times 10 divided by 8. Times 12.011. So I get 58.224 grams of carbon. Okay, so what do I know? the chlorine's going to run out, and the moment the chlorine runs out, I've got about 58 grams of carbon made. So I'm going to have leftover C10H16, but I want to figure out how much of the hydrochloric acid was created as well. So I'll do another one of these. 275 grams of Cl2, 7912 grams Cl2, 1 mole Cl2, 8 moles Cl2, 16 moles HCl, 1 mole HCl, and so 35.456 plus 1.00795 equals 36.464 grams of HCl. Okay, so 275 divided by that 70 number. Times 36. So 283 grams of HCl. Okay. I'll do this one a little bit different than we did the last one, and I'm going to do the 275 again. .912 grams of chlorine, 1 mole chlorine, 8 moles chlorine, 1 mole C10H16, 1 mole C10H16, and 136.237 grams C10H16. What's this last calculation going to do for me? Say again? It's going to tell you how much of the C10H16 is needed to react with that 275 grams of chlorine, and then I can just subtract from the 125 that I started with. Times 136.237. Well, that's a problem. Divided by, there we go. So I only needed 66 grams of this. I had 125 grams, so 66. So what's left in the container when I'm finished with this is, I should write 59 grams of the C10H16, 238 grams of hydrochloric acid, and 58.224 grams of carbon. Why are we not talking about this number right here that I've circled? It's a what if. And this what if isn't correct because this is saying if I had 125 grams of that C10H16, I could make 110 grams of carbon if I had enough chlorine gas, but I don't. So I will not be able to make that amount of carbon in this circumstance because I'll run out of chlorine gas the second I've made 58 grams of carbon. Somebody want to give me a decomposition reaction? All right. Switch to another one. Okay. How about a combination reaction? How about F2? You okay with that? Double replacement reaction? The double replacement reactions are all what kind of compounds? They're all salts. One salt mixing with another salt, creating two more salts. What's important about the first two? Salts, the salts in the reactant. Any salts? Say again?
I was gonna say maybe they should be soluble.
They have to be soluble salts for them to work, for sure. So, give me one soluble salt. Say again? KCl? All right, great. KCl. That is aqueous. What else we got? Give me another soluble salt. What's that going to make? Okay.